It didn't work this morning, let's just put it that way. Okay. So these are classic sort of problems. When I say classic, then actually if you want to on the front of the say, Unit 2 exam, you can, because you're going to see something here on Unit 2 exam. But you could say that about all the parts that we cover. Okay? Okay, so this sort of problem actually deals with compounds. And basically, it's taking a compound and saying, for each element, what is the weight percent of that element in that compound? There's weight percent composition problems. Okay? So in order to work this problem, somebody gives you the chemical formula, for instance, water, H2O, and they say, well, okay, that's all great, but what weight in a water molecule, what percent is hydrogen, what weight percent is hydrogen, what weight percent is oxygen? Okay? So they will give you the chemical formula. So we're going to do an example, and then I'll show you how I would kind of lay this problem out here in a minute. Okay, but walk through it, the slides. Acetone, each acetone molecule has 3 carbons, 6 hydrogens, and 1 oxygen. So when we do a percent elemental composition problem, for instance, the way this is going to work in the end, we are going to end up with weight percent carbon, okay, weight percent hydrogen, and weight percent oxygen. Okay, that's what we're doing. That's our goal. So to work this, and there's a couple different ways to work it, but I'm going to show you on the basis of 1 mole of compound. And for that reason, I'm going to knock out the overall mass of 1 mole of the compound, the molar mass of the compound. So you guys got some work at doing that for the homework that you handed in. So we look up carbon, hydrogen, and oxygen on the periodic table. We take 3 times 12.01, because there's 3 carbons. We take 6 times 1.008, because there's 6 hydrogens. And then we take 1 times 16.00, because there's 1 oxygen. And so the molar mass of that compound is 58.08 grams per 1 mole. So we can then, if we set as our basis 1 mole of the compound, then by this we have 58.08 grams of compound, because it's 1 mole of compound. And of that 58.08 grams in our basis that we set aside, the mass set aside for carbon, the mass of carbon in that 1 mole of compound is 3 times 12.01 grams, or 36.03 grams. Okay, that's the mass of carbon. The mass of hydrogen is 6 times 1.008 grams, or 6.048 grams. And the mass of oxygen is 1 times 16.00 grams, 16.00 grams. So to kind of put this in perspective, by golly, these masses will add up to a total of 58.08 grams. Now it doesn't look, well, it never did look too bad, but can you see how I can get weight percent carbon by simply taking this number divided by that number? And I can get weight percent hydrogen by taking this number divided by that number, and weight percent oxygen, that number divided by that number. Yep, that's exactly what I'm going to do over here. So weight percent carbon is that 3 times 12.01 grams of carbon divided by 58.08 grams of compound. One of the things about your exams that I graded, I like that, like if you abbreviate something, you know, in the problem, like for instance, if you wanted to go with CPD for compound, since we're only dealing with acetone, instead of writing C3H6O, you could do that. You probably just want to state that's what you're doing. So We need to round correctly. There's no uncertainty brought by the 3, but there is by the 12.01, and there is by the 58.08, so 4 sig figs. Okay, so the weight percent of carbon is 62.04%. We'll do a similar thing for hydrogen. The weight percent of hydrogen is 6 times 1.008 grams of hydrogen divided by 58.08 grams of compound, or C3H6O. To get it in parts per 100, it's times 100%, or times 100. And it looks like 4 significant figures again, so 10.41% is the mass percent of hydrogen. And last but not least, for oxygen, it's 1 times 16.00 grams of oxygen divided by 58.08 grams of compound, C3H6O, times 100. I'm going with 4 significant figures. I got 27.55%. So on a slide coming up I have in a minute, by golly, those weight percents should add up to be 100, shouldn't they? Yeah. That's a good way to check your problem. So it's kind of straightforward. Given the formula for a compound, we can go to weight percent. And they do add up to 100. So now I want to show you, if I was working this problem, I'm kind of into columns, and you'll kind of see that here in a minute for another type of problem. But I probably would do it something like, my work would look something like this. No. Oh, there it goes. Ah, isn't that weird? Came up for me, not for you. PowerPoint Office 2013 is really just, I find so irritating. I like it in some ways, in other ways I don't. So I mentioned the columns thing, okay? So the problem we just worked is here. This is the problem we just worked. Okay, and I got the same answer, and I probably would take these 2 columns, and if I was being a little more conservative, these 2 columns would end up kind of over here. So, it's got a mind. Dun-dun-dun. There's the first one. And I do have these handy to show you. I didn't add anything to them, but they're just exactly the problem we did with acetone, but different compounds. Sorry, 3, 2, 4. Oops. So here's 23 and 24. So for 23, you'll have a weight percent of carbon, weight percent of hydrogen, weight percent of nitrogen, weight percent of oxygen. I understand that you can get by difference the last weight percent, but I would suggest you not do that and instead add up all your weight percents and make sure they add up to 100. Okay, but you're thinking of it right if you think, well, I can just get 3 of the 4 and then knock out the 4 by difference. Okay. The next one is pretty straightforward. Any questions about those? So you have a weight percent of copper, carbon, hydrogen, and oxygen. All right. Dun, dun, dun. So I've kind of mentioned this idea that there's actually 2 types of chemical formulas. So chemical formulas give the formula of a compound, right? Chemical formula. There are molecular formulas, which is what we're most used to. I say that molecular formulas are like the real deal, okay? And then there are empirical formulas for the same compound. Empirical formulas. And here in a minute, after we talk about what an empirical formula is, kind of the way ionic compounds are written, ionic compounds are almost always written as empirical formulas. So what empirical formulas are, or sometimes empirical formulas can be reduced from the molecular formula. Okay, so what empirical formulas do is give not the real deal necessarily, but the relative amounts. Okay, so if you have, and I'll show you an example here. Again, empirical formulas, I'll put it this way. Sometimes, and I'll do some examples here, sometimes you can reduce a molecular formula into an empirical formula, sometimes. So here's what that looks like. So here is an assortment of 6 compounds. Okay, the molecular formula is given in each case. But for instance, butane has 4 carbons and 10 hydrogens. Okay, so actually we can reduce that. Do you see where we can divide the 4 and the 10 by 2? And so we end up with a 2 and a 5. So C4H10 and C2H5 give the same relative numbers of carbon and hydrogen atoms. The C4H10 is just kind of a scaled up version. C4H10 is the real deal of butane, okay? But I'm going to show you that sometimes butane actually, you get a lot of information just recognizing that for every 2 carbon atoms you have 5 hydrogens, okay? So sometimes you can reduce the molecular formula to get an empirical formula. Now the next one, water, I don't see it happening, right? Okay, so water does have a molecular formula and an empirical formula, but they're the same. Hydrogen peroxide, this is my Santa Claus molecule, right? Of course, hydrogen peroxide, the real deal is for every molecule you have 2 hydrogens and 2 oxygens, but we can divide 2 and 2 by 1 and get, 2 and 2 by 2, excuse me, and get 1. So it's ho, 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 yes. Okay. Hydrazine, the real deal is 2 nitrogens and 4 hydrogens. We divide each subscript by 2, and it can be reduced to NH2. These last 2 are my favorite, and they're on purpose, okay? So acetylene, we can reduce to CH, right? And benzene, we can reduce to CH. Yep. 2 totally different compounds, okay? But they have the same empirical formula, different molecular formulas, okay? I would say if I was writing, put it this way, if I was writing some sort of chemical reaction, I'm going to go with their molecular formula, okay?
I'm wondering what the point is then to have an empirical if it can be confused like that. We haven't gotten there.
We're getting there, but yeah, we're getting there. One overall, it's not a benefit or something you would do with this, but one of the things is called combustion analysis. It's another type of chemistry problem that we probably won't get to until maybe even next week. It's combustion analysis part 3. We're going to pull part 3 and move on to part 4 so we can kind of get down the road for your labs. But in combustion analysis, basically you take a hydrocarbon and you burn it, okay, and you end up with carbon dioxide and water, okay? And basically with combustion analysis, all you can get is the nuts and bolts of the relative amounts of carbon and hydrogen. You can't get past just relative amounts of carbon and hydrogen with combustion analysis. Benzene and acetylene would give you the same results with combustion analysis. Okay, so that's one thing. And maybe it'll become more clear what's good with an empirical formula. So when I kind of put the things up, maybe I didn't, but when we had molecular compounds and ionic compounds, kind of a list going on, we said that we call ionic compounds formula units, and they form crystal and lattice structures, ionic compounds, and the best you can do is basically grab a cation and an anion, and basically you have your lowest number of repeating units. So it really already is reduced, usually. So empirical formulas and weight percents, they actually give similar information. Empirical formulas are just giving you the nuts and bolts. Empirical formulas of what elements you got there and the relative number of atoms. That's the empirical formula, nuts and bolts. Okay, weight percent is giving you relative amounts, but it is on weight, not on atom basis. So percent elemental compositions that we did with acetone, the weight percent problems, weight percent gives you relative amounts on masses. The empirical formula gives you even a reduced amount, maybe even reduced information, relative amounts of atoms or moles of each element. So now, actually kind of related to that, we can do another type of problem. Here we go. So we actually, in the first problem with acetone, we went from the formula to weight percent. I'm going to show you how you can go from weight percent to a formula. Okay? From weight percent to a formula. Now the formula you first go to will be the empirical formula. Okay, that's all you can get from weight percent. That's like kind of what you get with combustion analysis. It's kind of bare bones. Determine empirical formula from the percent composition. Okay, so let's do one. We do a lot of defining your basis up front. To me, what a basis is basically you have set the stage for the problem. That's what a basis is. You're saying, what is most convenient to work this problem? So we're going to do a basis again. We did one earlier when we said our basis was 1 mole of compound, 1 mole of acetone, and then went from there. Okay, so our basis here actually is going to be 100 grams of this compound. So I go with 100 grams, see all of those percents turn into grams. That's exactly why we choose as our basis 100 grams. So if our basis is 100 grams of the compound, actually 100.0 grams, 4 significant figures, okay, then all I did here in that box is to take those percents and turn them into grams. So if I'm going with 100 grams of compound, 100.0 grams of compound, that means I have 53.3 grams of carbon, 11.2 grams of hydrogen, and 35.5 grams of oxygen, just picking off the percents. My first step, and there might be another way to work this if you've been taught another way to go from weight percents into empirical formulas. But my first thing is then to turn those grams into moles. I'm going to turn those grams into moles. So I'm actually going to have to use the molar mass of the individual elements. Okay? So the number of moles of carbon, I have to use the molar mass of carbon. So my first term is going to be that 53.3 grams of carbon over 1. My next term is going to be 1 mole carbon over 12.01 grams. So that's the molar mass of carbon. Of course, grams cancel, we're left with moles. Round to 3 significant figures. Then, in that 100 grams of compound, I have 4.44 moles of carbon. And then I do the same thing for the other 2 elements. So the next element is hydrogen. I have 11.2 grams of hydrogen over 1. If I go with my next term, for the molar mass of hydrogen is 1.008, so I put 1 mole of hydrogen over 1.008 grams of hydrogen. So round to 3 significant figures, I have 11.1 moles of hydrogen. Then we do one more. For oxygen, it had 35.5 grams of oxygen. The molar mass of oxygen, 16.00 grams per mole, so 35.5 grams times 1 mole oxygen over 16.00 grams of oxygen. Rounded to 3 significant figures, I have 2.22 moles of oxygen. Now, I know it's not right. We're not done. But in a way, the way I think of this is we have just come up with subscripts for carbon, hydrogen, and oxygen. I could say that there are 4.44 moles of carbon for 11.1 moles of hydrogen for 2.22 moles of oxygen. Okay? I know that doesn't look right? They need to be whole numbers, right? But that's kind of what we have going on here. So notice that I based this on 100 grams. Well, if I would have taken 200 grams, wow, I would have gotten 8.88 subscript for the carbon, 22.2 subscript for the hydrogen, and 4.44 subscript for the oxygen, right? I scale that up. I'd get the same relative amounts, right? Okay, I just set as my basis 100 grams. Of course, the reason I did that is they were already parts per 100, so it made our life easier. Okay, so that's setting as the basis 100 grams of compound. So the next step actually kind of deviates from what I would do. On this piece of paper, if you look at my answer keys for this sort of problem, you're going to see kind of like the column thing you saw for coming up with weight percents. I usually say element, and I write carbon, hydrogen, oxygen, okay, and then I write maybe mass, and I'm not going to write it again here, but remember we based upon a 100 gram sample, that was the mass, and then I come up with the moles column, okay, and I'll go ahead and write down the moles we came up with. We came up with 4.44 moles of carbon, 11.1 moles of hydrogen, 2.22 moles of oxygen. Okay, that's my relative moles. Now, the reason I like the column is because what you're going to see on the next thing is to basically, in order to clean it up, I'm going to divide by the smallest number. So actually, that's kind of why I like the column. So I usually will make another column here so that it says divide by 2.22. And when I run things through the mill, dividing by 2.22, I can do the first one in my head. Okay, so that looks like 2. The next one, is it 5? 11.1 divided by 2.22. Yep. Next one's 5. So you always divide by the smallest one. And of course, 2.22 divided by 2.22 is 1. Okay. Things kind of fall in line. Now, I'm going to show you there are sometimes some catches, okay? But you get those whole numbers that you're looking for. All I did was to kind of divide by the same number, okay, to keep the same relative amounts. By golly, and I'll show you the slide that kind of, right now, finally, we do have relative number of moles. We have 2 carbons. We have 5 hydrogens. And we have 1 oxygen. Okay, that actually is the formula of the compound. So, but what my slides do is kind of talk you through it just in a different way. It's the same process. 2.22 was our smallest moles we had. So actually, if we could come up with the relative moles of carbon to oxygen, which was oxygen is the 2.22. We divide that out and we recognize, by golly, for every 1 mole of oxygen you have 2 moles of carbon. We could pick on hydrogen then, and we could find out the moles of hydrogen per mole of oxygen, and that's that 11.1 moles of hydrogen divided by 2.22 moles of oxygen. Okay, and when we divide that out, we find that we have 5 moles of hydrogen for every 1 mole of oxygen. It's basically doing the same thing, but I kind of like the table approach. The table approach can help if, I'm going to show you an example where sometimes you need to do one more multiply through everything. And I just think it's easier to look at the table. But do you see where this is saying the same thing? This is saying it's carbon, hydrogen, oxygen. It's like, all right, so we're going with oxygen. For every 1 mole of oxygen, we have 2 moles of carbon and 5 moles of hydrogen. Same thing. Cho. All right. Voila! But now this is an empirical formula, not necessarily a molecular formula. It's an empirical formula. That's all you can get from just weight percents, which is pretty cool, though. Pretty darn cool.
Can you just multiply everything by 2, though?
You can scale it up, and we're going to do an example of that in a minute. What he's saying is if you know this compound has 4 carbons in it, you're like, oh, right, I know. If it has 4 carbons in it, then it must be C4H10O2, and you'd be right. Okay, exactly. So here's my, the example we worked came out just sweet. Like we got, 2.00, 5.00, It won't always be that right on the button, but it should be pretty darn close. I'm going to tell you, avoid rounding, okay? Avoid rounding, especially if you see, and I'm going to show some examples here. If you see a factor of 2 or 1/2, or if you see a factor of 4, or let's say 4 would be 0.25, 1/4, or if you see a factor of 3 or 6. 3 would be 1/3, and 6 would be, well, you'll see it here in a minute. 1/3 or 2/3, I guess I should say. Anyway, so avoid. I'll show you how you can fix those. So, for instance, let's say you came up with, you did however you're doing it, whether it's kind of the table method or just the individual kind of problems. You divided by the smallest, and you ended up with 1.5 moles to 1 mole. Don't round, okay? Basically, you need to scale that puppy up. You can get a whole number from 1.5 if you multiply it by 2. That's exactly what you need to do, and I'm going to do an example here where you need to scale it up. So that actually, if you multiply through by 2, you end up with 3 for every 2. Okay, so that's the relative number of atoms, or moles of atoms in that compound. So that would be kind of like a 2 or 1/2 sort of thing. Here's an example of kind of thirdsies, okay? As tempting as it is, if you end up with 1.33, okay, as tempting it is to just say it's 1-to-1, we can clean that up if we multiply by 3. If you take 1.3 times 3, things fall into place, okay? 1.3 times 3 is 4, okay? So again, if you take, and check on your calculator. So to clean up thirdsies, we multiply by 3, okay? To clean up halfsies, we multiply by 2. Here's an example. Here's that quarter I was talking about. So to clean up quarters, you multiply by 4. And so then we end up with 5/4, okay? So that's the thing you need to be aware of. And then the last example I have is where, again, we're kind of at thirds or sixths, however you want to think of it, thirds. So actually, we can multiply by 3 again. And you'll get a nice number in the numerator and a nice number in the denominator, 8/3. So kind of be looking for those. All right. So an example of where it came on the heels of be careful for these fractions. So that's what this problem is. So we're going to work this problem very similar to what we worked the other weight percent to in empirical formula. So we're going to take as our basis 100 grams of this compound, and we're going to knock out the empirical formula for CH, okay? So based upon 100 grams of the sample, we have 82.7 grams of carbon, 17.3 grams of hydrogen. So we're going to knock out the relative moles of each of them. we're going to take the 82.7 grams over 1, or grams of carbon over 1, times 1 mole of carbon per 12.01 grams, the molar mass of carbon. Round it to 3 significant figures, we get the moles of carbon. So the moles of carbon, 6.89 moles. We do the similar thing with the hydrogen, 17.3 grams of hydrogen over 1, times 1 mole of hydrogen per 1.008 grams of hydrogen. That's the molar mass of hydrogen. Round to 3 significant figures. Okay, so 17.2 moles of hydrogen. So I probably would have done that kind of in a table form. And so my table would look like this. Okay, where I had element, of course carbon and hydrogen. I'm just going to skip to the column we would come up with. Relative moles of carbon and hydrogen, 6.89 moles and 17.2 moles. And then I would go ahead and make another column. I would divide by 6.89, because that's what I know. I divide by the smallest. Of course, that leaves me relative moles of carbon as 1.00. And the other one, 17.2 divided by 6.89. Okay. The other one looks suspicious. 2.4, actually to 3 sig figs, be 2.50, right? Okay. So this is an example where I can't stop here. I need to make one more column or else clean it up in some way. So I usually make another column at the top. I just say times 2. And so that scales my carbon up to 2. And 2.5 times 2 is 5. Okay, so actually the answer is C2H5. They're kind of fun. So then my slides kind of do a similar thing, okay? Basically, again, I'm going to put moles of carbon in the denominator because it's the smallest. I recognize that actually I have if I divide 17.2 moles hydrogen divided by 6.89 moles of carbon, is equal to that 2.50 moles of hydrogen per 1 mole of carbon. And then I recognize I can't use those as subscripts, and I'm not going to round down or up for that 2.5. So I end up with multiplying both by 2, okay, which leaves it with multiplying both by 2, which leaves it with 5 moles of hydrogen for 2 moles of carbon. That's a lot to write down. So either way. So then for this one, you just need to turn that into your compound. Okay, so 5 moles of hydrogen for 2 moles of carbon. Same thing. Right? C2H5. Okay, so I don't know if this is a repeat slide. Okay. So one more twist on going from weight percent to a formula. We went from weight percent to the empirical formula. You can go from weight percent through the empirical formula all the way to the real deal, the molecular formula, if you know the weight of the molecule, if you know the molar mass of the compound. So you have to be given weight percents and molar mass. And I'll show you an example of that here in a minute. right now, actually. So remember, the empirical formula is what you get from weight percent. You can advance it to molecular formula if you also know the mass. Molar mass. Oh yeah, I forgot I put that in there. Okay, so we're not going to do this problem again, but a while back we actually did this problem where you have the weight percent, carbon, hydrogen, oxygen. Okay, based upon those weight percents, we came up with the empirical formula for the compound is C2H5O. So we did this already in your notes. So now the extra information given, so we can go ahead and go from the empirical formula to the real deal molecular formula, is the molar mass of the compound. So somebody said, all right, for the real deal compound, its molar mass is 90.1 grams per mole. Okay. So here's how you do that. Basically, you go ahead and take, well, first off, when we are trying to go from the empirical formula, it's kind of like we talked about a minute ago. When we are trying to go from the bare bones empirical formula, which is C2H5O, actually just recognize that we could have any sort of variation of that, where, for instance, it could be C4, H10O2, or it could just be multiplied by 3. It could be C6, H15O3 multiplied by 4. It could be C8, H20, O4. It could be any of those. So once we have the molar mass, like we have, that 90.1, we can go ahead and figure out basically what X is. How many repeating units are there in one molecule? So here's how this works. There's probably more than one way to skin this cat. We can actually knock out the molar mass of the repeating unit. Okay? The molar mass of the repeating unit, the molar mass of the empirical formula. Okay? And all we got to do is take the molar mass of the compound divided by the molar mass of that repeating unit. And that will tell you how many repeating units there are. Okay? And hopefully it's a nice round number. And actually this one is. So the empirical formula, C2H5O, we can come up with that unit mass. So 2 times 12.01 plus 5 times 1.008 plus 1 times 16.00. So the empirical formula repeating unit is 45.06 grams per mole. You probably already see if you double that, you get 90. Okay? So that's actually where we're going with that. To come up with how many repeating units there are in a molecule, we take that, the molar mass of the molecule, 90.1 grams per mole, divided by the molar mass of the empirical formula, 45.06 grams per mole. So by golly, we must have to basically multiply through by 2, and then we'll get what we need. So based upon that, we can go ahead and say that the molecular formula of this compound, based upon that weight percent and the molar mass of the molecule, is C4H10O2. We scaled it up by a factor of 2. So, I said it was coming. Yeah, and these are all good. I'm going to go ahead and take a look at these. I don't have any notes yet, but these are so similar to the ones we just worked. There's not a lot of twists, but darn. No, I'm just kidding. Okay. So they kind of go in pairs. These two, notice that you're just supposed to come up with the empirical formula given those weight percents. I would clearly, just like we've been doing in here, you know how I did a box? I said on the basis of 100 grams of sample, 100.0 grams of compound. That's exactly the basis you need to state in your problem. For 2 reasons. 1, it's the right thing to do. 2, you remind yourself, The next one looks like this. The last 2 are actually just like the last problem.
The
where you're given weight percent, you have to knock out the empirical formula, and then you're also given the molar mass of the compound, so you have to come up with the real deal. What is the molecular formula? And then this 38's the same way. Okay, so you're going to come up with the molecular formula through the empirical formula from the weight percent, just like we did. Okay? Awesome. That's all I got.